Hello, my name is Isabel Pinto, and I am going to be going over the Digital Sampling Lab report from AE 2610. My group is A10Y. So first we're going to talk about the introduction and motivation for this lab. Then we're going to go over procedure for week 2 and results, and then procedure and results from week 3, and finally the procedure and results from the individually developed experiment. So first, a quick introduction to waveforms and sampling theory. The Fourier transformation is used heavily in this lab, and this allows us to convert data from time-dependent data to frequency-dependent data, which is very useful when we're analyzing waveform data. And it'll allow us to identify multiple waves that have different frequencies, which are all put together in a single signal. So we will be using the first equation on the right there. We can also use the Fourier transformation to spot noise. Now, sampling theory and aliasing mean that it is very important to take enough samples so that we can get an accurate depiction of the waveform. We can use the Nyquist sampling theorem, which is the bottom equation there, which defines the required sampling frequency to accurately determine a waveform. As for aliasing, this is when higher frequencies show up as lower frequencies with low sample rates. So we want to avoid aliasing and we want to have an accurate depiction of the waveform, so that requires a high sample rate and a high number of samples. Now, with regards to motivation for this experiment, it was to understand digital data acquisition of time-varying signals. It will provide an understanding of sampling theory and introduce students to DAC systems. And finally, in a larger sense, there are many measurements which vary regularly with a specified period, for example, sound waves. So frequency-varying functions are useful in an analysis tool. Now let's move on to the procedure from week 2. First, we set up the DAC system. Then we identified the various tracks as different sorts of waveforms with different frequencies. Then we interpreted the power spectra for each of these different tracks. We examined the quantization error, and varied the record length and sampling rate to see the effect of aliasing and consider sampling theory. So then we observed aliasing, and we were able to examine noise and explore the use of the low-pass filter. The results here focus on the track analysis. As you can see, all of the tracks were identified, and track 9 had 3 total frequencies, one at 1,000, one at 100, and one at 10,000. During the course of this experiment, I observed that if you increase the sampling rate and the number of samples, you can generally eliminate aliasing. And if the wires are straightened or the wire insulation is increased, you see a reduction in noise. Now let's move on to week 3. So the first thing that we did for week 3, and this procedure, was to verify the microphone setup. We set up the tone generator, the DAC, and the function generator, and collected time history and power spectrum for 5 frequencies listed there as measured through the audio jack. And this was a basis from which we could compare to the time history and power spectrum as measured through the microphone. So those results, as you can see, are in this table here. We have an average relative response, which is the power of the microphone divided by the power with the speaker, of 3.02. A standard deviation of 0.633, and no specific relation between the frequency and the relative response. Now let's move on to the individual experiment. I was curious how distance affects the signal-to-noise ratio. The motivation for this is that having a clear relationship between noise and distance will be helpful to if you are trying to detect signals over a large distance. So the goal of the experiment was to find a relationship between SNR and a distance and find a mathematical relationship if possible. To do this, I set the record length to 5,000 samples, the sampling rate to 25,000 samples per second, and the recorder to continuous. This was to eliminate any possible chance of aliasing. I set the tone generator to 300 Hz at 50% volume and then held the microphone at a distance of 1 centimeter from the computer speakers. Then I recorded the power spectra from distances between 1 and 15 centimeters, incrementing by 1 centimeter, and leaving all other settings constant. The data that I gathered, these are the signal power at 300 Hertz, noise power, which is averaged over every other frequency. Then to find the signal to noise ratio, I use this equation over here, which gives us these values for SNR. Finally, we find these results. We see that signal to noise ratio decreases with an increase in distance. And I noticed that noise remained fairly constant across distance and found no clear mathematical patterns in the trend, and so more data is likely necessary for higher fidelity results. In conclusion, there was no clear mathematical pattern in the signal-to-noise ratio data, and our hypothesis supported that the signal-to-noise ratio decreases as distance increases according to the graph. In the future, I would like to perform the same test at different frequencies to find out if the signal-to-noise ratio is increased, decreased by frequency. But I did find that as I was doing the experiment, it was difficult to have the exact distance from the speaker and could have been off by 0.1 centimeters. That covers everything in the digital sampling lab report. Thank you for listening.